The knowledge of quantum mechanics, together with Einstein's theories of relativity, really gave us the modern world.
For decades, Albert Einstein's theories of relativity have been the cornerstone of modern physics, shaping our understanding of time, space, and the very fabric of the universe. Einstein's groundbreaking equations described how gravity warps space-time, how light bends around massive objects, and even how time slows down near powerful gravitational forces. His work has been tested time and time again, holding up as one of the greatest achievements in scientific history. But now, a groundbreaking discovery in the realm of quantum computing has sent shockwaves through the scientific community, challenging one of Einstein's most cherished beliefs about the nature of reality. At the heart of Einstein's philosophy was a deep discomfort with the seemingly strange and paradoxical world of quantum mechanics. In fact, Einstein famously said, "God does not play dice with the universe," expressing his skepticism about the inherent randomness of quantum systems. For Einstein, the universe was deterministic, a vast, elegant machine governed by predictable rules. Yet quantum mechanics introduced something fundamentally different: uncertainty, randomness, and particles that behave in ways that defy classical intuition. Now, with the advent of quantum computers, machines that operate on the very principles of quantum mechanics, scientists have achieved something extraordinary, an experiment that directly tests Einstein's assumptions about the universe, and the results are nothing short of astonishing. Before diving into the implications of this groundbreaking discovery, let's explore the history of this debate between Einstein and quantum mechanics. Einstein's skepticism toward quantum theory wasn't just philosophical, it was rooted in a scientific challenge to one of quantum mechanics' core ideas: entanglement. Entanglement is a phenomenon where two or more particles become so deeply interconnected that the state of one particle instantly affects the state of the other, no matter how far apart they are. Einstein derisively referred to this as spooky action at a distance, believing it violated the principle of locality, the idea that nothing can influence anything else faster than the speed of light. In essence, Einstein argued that quantum mechanics was incomplete. He believed there had to be hidden variables, unseen factors that would one day provide a classical explanation for the seemingly bizarre behavior of entangled particles. For decades, scientists sought to test Einstein's claims, leading to a series of experiments now known as Bell tests, named after physicist John Bell, who formulated a mathematical framework to evaluate whether hidden variables could explain quantum entanglement. Over time, these experiments consistently confirmed that quantum mechanics, not Einstein's hidden variables, was correct. But even as these results emerged, Einstein's legacy endured, and questions remained about the ultimate nature of reality. Fast forward to the 21st century, and quantum computing has revolutionized our ability to probe the mysteries of the quantum world. Unlike classical computers, which process information as binary bits, zeros and ones, quantum computers use qubits, which can exist in superpositions of states. This allows quantum computers to perform calculations and simulations that would be impossible for classical machines, making them ideal tools for testing the limits of quantum mechanics itself. And this is where the story takes an astonishing turn. In a recent experiment conducted using a state-of-the-art quantum computer, scientists have demonstrated a phenomenon that directly challenges Einstein's deterministic worldview. The experiment involved creating a quantum simulation of space-time itself, a groundbreaking achievement that allowed researchers to observe how quantum systems interact with the fabric of the universe. In this simulation, scientists observed something truly bizarre. Entangled particles not only appeared to communicate instantaneously across vast distances, but their interactions also seemed to influence the very structure of space-time. It was as if the entanglement process was actively reshaping the universe, creating ripples in the fabric of reality. This discovery has profound implications, suggesting that space-time itself may emerge from quantum processes rather than being a static backdrop for the events of the universe. What does this mean for Einstein's theories? At first glance, it might seem like a direct contradiction to relativity. After all, if quantum processes can influence spacetime in ways that defy classical intuition, it raises questions about the limits of Einstein's equations. But scientists are careful to point out that this new discovery doesn't render relativity obsolete. Instead, it suggests that relativity is just one piece of a much larger puzzle, a framework that works well at macroscopic scales but breaks down when we delve into the quantum realm. To fully understand the implications of this discovery, we need to explore the concept of quantum gravity, a field of study that seeks to unify Einstein's general relativity with quantum mechanics. For decades, physicists have struggled to reconcile these two pillars of modern science as their mathematical frameworks are fundamentally incompatible. Relativity describes the universe as a smooth, continuous fabric, while quantum mechanics reveals a world of discrete, probabilistic events. The recent findings from quantum computing provide a tantalizing glimpse into how these two frameworks might be connected. If spacetime emerges from quantum processes, as the experiment suggests, it could mean that gravity itself is a quantum phenomenon. This idea aligns with theories like loop quantum gravity and string theory, which propose that spacetime is composed of tiny, discrete building blocks. But the implications go even deeper. If quantum mechanics governs the very fabric of reality, it raises profound philosophical questions about the nature of existence itself. For instance, if spacetime is emergent, what lies beyond it? Could there be a deeper layer of reality, hidden from our current understanding, that gives rise to the quantum world? And if so, what role do we, as conscious observers, play in this process? This brings us to one of the most mind-bending aspects of the experiment: the role of observation. In quantum mechanics, the act of measurement plays a crucial role in determining the outcome of an event. This phenomenon, known as the observer effect, suggests that reality isn't fixed until it is observed. In the context of the recent discovery, this raises the possibility that our observations might not only influence quantum systems, but also the structure of spacetime itself. If this idea sounds like science fiction, consider this. Some physicists have proposed that consciousness itself could be a quantum phenomenon. According to this view, our minds are deeply interconnected with the quantum fabric of the universe, and our thoughts and perceptions may play a role in shaping reality. While this idea remains speculative, it highlights the profound questions raised by the latest findings in quantum computing. As we continue to explore the implications of this discovery, it's important to consider the practical applications of quantum computing. Beyond its potential to revolutionize our understanding of the universe, quantum technology has the power to transform fields like cryptography, artificial intelligence, and materials science. By harnessing the principles of quantum mechanics, we can solve problems that were once thought to be insurmountable, paving the way for innovations that could reshape society. However, with great power comes great responsibility. The same technology that enables us to unlock the mysteries of the universe also has the potential for misuse. Quantum computers could render current encryption methods obsolete, leading to concerns about cybersecurity and privacy. Additionally, the ability to manipulate quantum systems on a large scale raises ethical questions about the potential consequences of tampering with the fundamental building blocks of reality. As we stand on the brink of this new quantum era, one thing is clear: the discoveries we make today will have far-reaching implications for generations to come. Einstein's theories may not be the final word on the nature of reality, but they laid the foundation for the incredible progress we've made in understanding the universe. And while quantum computing has revealed new mysteries that challenge our classical intuition, it also offers a powerful reminder of the beauty and complexity of the cosmos. In the end, the story of Einstein and quantum mechanics is not one of conflict but of curiosity, a testament to the power of human ingenuity and our unrelenting quest to unravel the secrets of the universe. As we continue to push the boundaries of knowledge, we honor Einstein's legacy not by clinging to his ideas, but by daring to question them, just as he dared to question the ideas of those who came before him. Quantum computing has not only challenged Einstein's deterministic worldview, but also opened the door to some of the most profound philosophical and practical questions humanity has ever faced. The experiment in question, where entangled particles appeared to reshape spacetime itself, raises issues about the very nature of cause and effect. In classical physics, events follow a predictable sequence. One event causes another in a clear linear chain. But in the quantum world, this tidy concept of causality begins to break down. Scientists have speculated for years that within the quantum realm, time itself may not exist in the way we traditionally understand it. Events in quantum mechanics can appear to occur out of order or even simultaneously. This phenomenon, known as quantum causality, could mean that the fabric of the universe doesn't rely on a strict timeline of events, but operates instead in a web of probabilities. The implications of this are staggering. If time as we know it is merely a macroscopic illusion, an emergent property of quantum interactions, it could mean that our understanding of the past, present, and future is fundamentally flawed. Imagine a world where events don't have a fixed sequence, where cause and effect can be reversed or intertwined. Such a reality would force us to rethink not only physics, but also concepts like free will, memory, and even consciousness itself. What's more, these findings align with emerging theories that spacetime may not be a continuous fabric, but rather a discrete, pixelated structure. Just as digital screens display images composed of individual pixels, the universe may be composed of tiny, indivisible units called Planck lengths. These are the smallest measurable units of space and time, representing the scale at which classical physics gives way entirely to quantum mechanics. Quantum computers, by operating at these infinitesimal scales, have given us unprecedented access to this hidden structure of the universe. In fact, some researchers believe that quantum computers could eventually be used to simulate entire universes at the Planck scale, allowing us to observe how spacetime emerges from quantum processes. Such simulations would be more than just scientific tools. They would be windows into the fundamental nature of reality itself. But this raises an even more unsettling question. If spacetime is emergent, what is it emerging from? Could there be a deeper layer of reality, one that exists beyond our current understanding? Some physicists have proposed that our universe might be a hologram, a three-dimensional projection of information encoded on a two-dimensional surface. This holographic principle suggests that everything we perceive, matter, energy, even the passage of time, is a kind of illusion, a shadow of a deeper, more fundamental reality. Quantum computing experiments like the one we're discussing have provided indirect evidence supporting this idea. By studying the behavior of entangled particles, scientists have observed patterns that resemble those found in holographic systems. These patterns suggest that the interactions of quantum particles may be governed by principles that extend beyond the confines of our familiar three-dimensional world. This leads us to a profoundly philosophical question. If the universe is a hologram, who or what is projecting it? Is there an underlying mechanism, a cosmic projector, that gives rise to our reality? And if so, could we ever hope to understand or interact with it? Some researchers have speculated that the quantum processes we observe could be the result of computational processes occurring in a higher dimensional realm. In this view, the universe itself might be a kind of quantum computer, processing information at a scale far beyond human comprehension. If this idea sounds like science fiction, consider the work being done in the field of digital physics. Digital physics is a branch of theoretical physics that explores the idea that the universe operates like a vast, complex computational system. According to this perspective, everything in the universe, from subatomic particles to galaxies, can be described as bits of information, akin to the ones and zeros used in classical computers. Quantum computers, with their ability to process information in superpositions of states, have given us a glimpse of what such a computational universe might look like. In fact, some scientists believe that quantum computers could eventually be used to test the hypothesis of digital physics, providing experimental evidence for the idea that the universe is fundamentally a system of information processing. But if the universe is a quantum computer, what does that mean for us as conscious beings? Are we merely programs running within this cosmic system? Or do we have some unique role to play in the unfolding of reality? These questions bring us to one of the most controversial and intriguing areas of quantum mechanics: the relationship between consciousness and the quantum world. As mentioned earlier, the observer effect in quantum mechanics suggests that the act of measurement influences the outcome of a quantum system. But what exactly constitutes an observer? Does it have to be a human being, or could any interaction with the environment qualify as a measurement? And if human consciousness does play a special role in shaping quantum reality, what does that say about the nature of the mind? Some physicists, such as Roger Penrose, have proposed that consciousness itself might be a quantum phenomenon. According to Penrose's theory of orchestrated objective reduction, OR, the brain's microtubules, tiny structures within neurons, operate at the quantum level, allowing consciousness to emerge from quantum processes. If this theory is correct, it would mean that our thoughts and perceptions are deeply interconnected with the quantum fabric of the universe. This idea has profound implications for our understanding of free will, creativity, and the nature of existence. If our minds are quantum systems, it could mean that our choices and actions are not entirely deterministic, but are influenced by the same probabilistic principles that govern quantum particles. In other words, free will might not be an illusion, but a fundamental aspect of the quantum universe. However, this view also raises unsettling questions. If consciousness is a quantum phenomenon, could it be possible to simulate or even replicate it using quantum computers? Some researchers believe that advanced quantum computers could eventually be used to create artificial intelligence systems with consciousness-like properties. Such developments would force us to confront ethical questions about the nature of life, identity, and the rights of artificial beings. Moreover, the idea that consciousness is a quantum phenomenon could have implications for our understanding of life after death. Some researchers have speculated that if consciousness is rooted in quantum processes, it might be possible for some aspect of the mind to persist beyond the death of the physical body. While this idea remains highly speculative, it highlights the profound philosophical and spiritual questions raised by the latest discoveries in quantum mechanics. As we continue to explore the quantum realm, it's clear that we are only scratching the surface of a vast and mysterious landscape. The discoveries made possible by quantum computers have challenged our understanding of time, space, and reality itself, forcing us to confront questions that were once the domain of philosophy and metaphysics. But these questions are not merely abstract. They have real-world implications for the future of science, technology, and society. Quantum computers have the potential to revolutionize fields ranging from medicine to cryptography. But they also raise concerns about the ethical and existential risks of tampering with the fundamental building blocks of reality. As we stand on the brink of this new quantum era, one thing is certain: the discoveries we make today will shape the future of humanity in ways we can scarcely imagine. Einstein may have been wrong about certain aspects of the quantum world, but his legacy as a scientist and thinker remains a testament to the power of curiosity and the human spirit. Ultimately, the story of quantum mechanics is not one of conflict, but of exploration, a journey into the unknown that challenges us to question our assumptions and expand our horizons. As we continue to unravel the mysteries of the universe, we honor the legacy of Einstein and all those who have dared to ask the big questions, paving the way for a deeper understanding of reality itself. Quantum computers, unlike classical computers, have revealed a far stranger universe than we ever could have anticipated. These advanced machines are not merely tools of calculation. They are windows into the underpinnings of reality. But what if their very existence poses questions that humanity may never fully comprehend? Or worse, questions we are too frightened to ask. One of the most striking aspects of recent quantum research lies in how these machines simulate phenomena at the Planck scale. Imagine a world where reality becomes pixelated, where space and time dissolve into a granular grid of discrete points. This pixelated nature, theorized by many physicists, suggests that spacetime itself is not continuous but a finite, computational construct. Quantum computers now give us the tools to peer into this grid. Simulating the interactions of particles at these scales, researchers have begun to uncover patterns suggesting an underlying code within the very laws of physics. But here's the disturbing part. Some researchers claim the patterns resemble error-correcting codes, like those used in digital communication systems. This resemblance has fueled the controversial idea that the universe operates as a simulation. Physicist James Gates, a prominent voice in theoretical physics, once pointed out that certain equations governing supersymmetry include embedded codes that are identical to those used in computer browsers. The implications of this idea are staggering. If we live in a simulated reality, who or what is running the simulation, and why? Expanding upon these revelations, quantum computing experiments continue to deepen the mystery. Consider this: quantum entanglement, a phenomenon Albert Einstein once dismissed as spooky action at a distance, suggests an interconnectedness between particles that defies classical logic. What one particle knows, another particle knows instantly, regardless of the distance separating them. This non-locality has been experimentally confirmed countless times, and it fundamentally challenges our understanding of space and time. The notion that information can be exchanged instantaneously across vast distances leads us to question whether the universe operates on a framework far beyond what our senses perceive. Some theorists suggest that the universe behaves like a hyperdimensional quantum network. In this network, our three-dimensional world may just be one layer of a far more complex reality. Quantum computers allow us to simulate this network, revealing its intricate dynamics and pushing us closer to uncovering its true nature. But this raises the question: what lies beyond the simulation? If quantum computers are capable of cracking the code of reality, could they also expose the limits of the simulation itself? Imagine a scenario where scientists run a quantum simulation so powerful that it reaches the boundaries of its own framework. Would this cause the program running our universe to crash or reset? And if so, what would happen to us as conscious beings within this framework? These unsettling questions are no longer confined to the realm of science fiction. Leading figures in physics, such as Michio Kaku and Neil deGrasse Tyson, have openly discussed the simulation hypothesis as a legitimate topic of scientific inquiry. Tyson once speculated that the odds of us living in base reality might be 1 in a billion. Kaku, meanwhile, has suggested that future civilizations might use quantum computers to create simulated universes indistinguishable from our own. But what if we are not the creators? What if we are the creation? The simulation hypothesis forces us to confront profound ethical and philosophical dilemmas. If we are living in a simulation, does that diminish the meaning of our existence? Or does it suggest that our actions have greater significance, as they might serve a purpose beyond our comprehension? Moreover, if we were to discover undeniable evidence of the simulation, how would society react? Would this knowledge lead to enlightenment or chaos? Quantum computers have also reignited debates about the nature of consciousness and its role in shaping reality. At the heart of quantum mechanics lies the observer effect, where the act of observation influences the outcome of a quantum system. This phenomenon suggests a profound link between consciousness and the physical world. But what does it mean for consciousness to collapse a wave function? Is the mind a passive observer of reality, or an active participant in its creation? Recent experiments using quantum computers have pushed this question to new heights. By simulating complex quantum systems, researchers have observed instances where the system appears to choose its state based on the presence or absence of an observer. These findings hint at a universe where consciousness is not merely an emergent property of the brain, but a fundamental aspect of reality itself. In this view, the mind may act as a bridge between the quantum and classical worlds, shaping the very fabric of existence. If this is true, the implications are staggering. Could consciousness itself be a quantum phenomenon, existing beyond the confines of the brain? Some physicists have proposed that consciousness arises from quantum processes occurring in microtubules within neurons, a theory championed by Roger Penrose and Stuart Hameroff. If quantum computers could simulate these processes, they might unlock the secrets of the mind, allowing us to explore the nature of thought, emotion, and perception in unprecedented detail. However, such advancements come with significant ethical concerns. If we can simulate consciousness, could we also create artificial beings with conscious experiences? And if so, what rights would these beings have? Would they be considered sentient? These questions are no longer hypothetical. They are rapidly becoming central to discussions about the future of artificial intelligence and quantum computing. Moreover, the discovery of quantum processes underlying consciousness raises profound questions about the nature of life and death. If the mind operates at the quantum level, could it persist in some form after the death of the body? While this idea remains speculative, it has captivated the imaginations of both scientists and philosophers. Some have even suggested that near-death experiences, where individuals report visions of light or feelings of interconnectedness, might be explained by quantum phenomena within the brain. As we delve deeper into the quantum realm, we are forced to confront the limits of our understanding. Quantum computers have shattered the boundaries of classical physics, revealing a universe that is stranger and more complex than we ever imagined. But in doing so, they have also exposed the fragility of our worldview. The discoveries we make today challenge us to rethink our place in the cosmos and our relationship to the unknown. The unsettling truth is that quantum computers are not just tools for solving equations. They are instruments of discovery that force us to confront the most profound mysteries of existence. They reveal a universe that is not a static deterministic machine, but a dynamic, interconnected web of possibilities. And in this web, we are not passive observers, but active participants, shaping reality through our actions, choices, and consciousness. But as we push the boundaries of what is possible, we must also grapple with the ethical and existential risks of this new era. Quantum computers hold the potential to revolutionize science, medicine, and technology, but they also raise questions about the nature of power, control, and responsibility. Who will wield this technology and for what purposes? Will it be used to benefit humanity or to exploit and manipulate? And what happens if the very act of probing the quantum realm destabilizes the delicate balance of reality? These questions remind us that with great power comes great responsibility. As we venture into the quantum unknown, we must proceed with caution, humility, and a deep respect for the mysteries of the universe. For in the end, the true significance of quantum computing may not lie in the answers it provides, but in the questions it forces us to ask. The journey into the quantum frontier is just beginning, and its implications will ripple across science, philosophy, and society for generations to come. As we stand on the precipice of this new era, one thing is clear: the discoveries we make today will shape the future of humanity in ways we cannot yet imagine.